So let's get started. In today's lecture, we're going to continue our discussion regarding the asphalt cement, and also today we're going to talk about the asphalt concrete. So last time you mentioned that the asphalt binder is produced in several grades or classes, and we have four methods for classifying the asphalt binders. We have the performance grading, the PG. This method is going to depend on the performance only, and we have the penetration grading. This method depends on the penetration test mainly, and we have the viscosity grading. This one is going to depend on the viscosity, and we have the viscosity of the H residue. Last time we talked about the penetration grading. We said that we have this criteria in order to select in order to classify the asphalt binder, and we talk about the requirements and what's used for. If the cement binder is classified as 6070, then what's going to be used for. And we talk about the local companies through which you can buy the asphalt cement or the bitumen. Also, they have the specification for their asphalt binder. And we talked about only introduction about the performance grading. This method, it has been introduced because of the limitation in the penetration grading and the viscosity grading. So today we are going to talk about how to understand the performance grading. So the current PG system, before we buy the asphalt cement, you are gonna see that they are going to write PG. So PG refers to performance grade. Then it's going to be followed by maximum and the minimum pavement surface temperature. So for example here, we have PG 52 minus 28. The first number here for the maximum temperature the asphalt binder can support. A minus 28 here, this is the value of the minimum temperature the asphalt cement can support. So this one is the maximum and this one is the minimum. Okay, that means the height, the maximum temperature is 52. This type of asphalt can support up to 52 degrees Celsius, and it can also support up to minus 28 degrees Celsius. So here another example, PG 64 minus 22. It means that it can support up to 64 degrees Celsius, and also it can support up to minus 22 degrees Celsius. This one is the maximum, and this one is the minimum. Okay, always the minimum or the second number is going to be in a negative temperature. So in order to select my asphalt that is going to suit my needs, I need to measure the maximum temperature and the minimum temperature, and then upon those values, I'm going to select the suitable type of asphalt binder according to the PG system. So how I'm going to measure the temperature, the maximum temperature is going to be measured 3/4 inch below the pavement surface, because we know that the deeper we go down, the temperature is going to be higher. So that is why I need to measure the temperature about 3/4 inch below the pavement surface. While the minimum temperature, because we know that the surface is going to be cooler than the lower layers, then the minimum temperature is going to be measured at the pavement surface. Then if you know the maximum and the minimum, then you are going to select your asphalt on that. So for example here, we have a map which has been made in order for you to select the suitable type of the asphalt binder according to the performance grading, according to the PG. Okay, so for example, if you are gonna use asphalt in Medina city, then you are gonna use PG 70 minus 10, which means that the asphalt is going to support maximum temperature 70 degrees Celsius, and is going to support minimum temperature minus 10 degrees Celsius. So nowadays you are not going to measure the maximum temperature and the lower temperature because you already have these maps, and through this map you are going to directly choose the suitable type of cement binder. So let's say that I don't know the maximum and the minimum temperature. Then I need to measure the maximum temperature at 3/4 inches and the minimum temperature at the pavement surface each year. So here, then you are gonna go to this table here. This table is going to show me the binder grades in the performance grade specifications. So this is going to work like that. First, I have the higher temperature, and this one, it has increment of 6 degrees Celsius. So if this one is PG 46, then I'm going to add 6. Then I'm going to have PG 52, and so on, up to the last one here. So here I have the high temperature, and here I have the low temperature. First, I'm going to choose the high temperature. Let's say that I measure the temperature, and the maximum temperature came out to be 60 degrees Celsius. Then I'm going to look for 60 degrees Celsius. So 60 degrees Celsius is between 58 and 64. Then in this case, I'm going to round to the above the maximum temperature. So if my maximum temperature is 60 degrees Celsius, then I'm going to use 64 degrees Celsius. Okay, I'm going to choose something higher, because if I'm going to choose something lower, then I'm going to have a problem. Okay, because the maximum temperature is 60, and this one support up to 58 degrees Celsius. So I'm going to have a problem. So always, when I'm going to choose the high temperature, I'm going to round above the maximum temperature, above the maximum temperature. Then I'm going to choose this one, PG 64. Then let's say that the lower temperature came out to be minus 20. So minus 20 between minus 16 and minus 22. So it's located here. In this case, I'm going to round to below the minimum temperature. If this one is minus 20, then I'm going to select minus 22. Okay, because if I'm going to choose minus 60 and the maximum, the minimum temperature is minus 20, then I'm going to have a failure. So I'm going to choose minus 22. So finally, my PG is 64 minus 22. This is how I'm going to choose my temperature from the table if I know the maximum and the minimum temperature. We have another problem regarding this, because let's say that I measure the maximum and lower temperature in 2020, okay? But maybe in 2019, I have different values, right? Of course, I'm going to have different values. Also in 2018, I'm going to have different values. So in this case, what should I do? So in this case, I'm going to use the statistical models. I'm sure most of you, they took statistical and probability course, or they are taking now statistical course. So we are going to gather a data. Let's say that I'm going to gather a data for the past 20 years, from 2000 to 2020. I'm going to gather the maximum and minimum temperature for the past 20 years. Then I'm going to have a data for the maximum values and a data for the minimum values. Since I have a data, then I will be able to determine the mean value and the standard deviation, right? So I'm going to determine the mean value and the standard deviation for the maximum values. And similarly, I'm going to determine the mean and the standard deviation for the minimum values, okay? So I'm going to represent this as normal distribution. So a normal distribution is going to be considered for the maximum values and also for the minimum values. So I'm gonna determine the mean and the standard deviation for this, assuming that I have normal distribution. Similarly, for the low values or the minimum values, I'm going to represent this by normal distribution. I'm going to determine the mean. I'm going to determine the standard deviation. So let's see example here. Assume that according to the maximum temperature or the high temperature, the mean came out to be 56, and the standard deviation is 2. And for the low temperature, the mean came out to be minus 23, and the standard deviation came out to be 4 degrees Celsius. So in this case, we are going to use the statistical model formula based on the normal distribution. In this formula, we are going to say that the Tmax, the maximum temperature that I'm going to select, should be more than or equal the mean value plus Z times the standard deviation. We know that the Z depends on the probability or the reliability here. We have a certain table in statistical method. We have a certain table for Z. If you know the probability or the reliability here, you're going to be able to know the value of Z. And if the value of the reliability is 98%, then the value of Z is going to be 2. When the reliability or the probability is 50%, then the value of Z is going to be 0. So the first job here, we need to determine the binder cement according to the 98% minimum reliability. Okay, so in this case, the value of Z is going to be 2. I'm going to use this equation here in order to determine Tmax. So Tmax should be more than or 56 plus, since this one is 98%, then the value of Z is going to be 2. So it's going to be 2 times 2. So I'm going to have 56 plus 4, which is 60. So the temperature should be more than or equal 60. Then I'm going to go to the table again. 60 is located here. So which means that I'm gonna choose PG 64. So the maximum temperature, I'm gonna use PG 64. PG 64 is more than 60. Then I'm going to solve the low temperature. I'm going to substitute here. I have the T minimum should be less than or equal mu minus Z times standard deviation. So mu is minus 23. The value of Z is going to be 2. The value of the standard deviation is 4. Then I'm going to have minus 23 minus 8, which is minus 31. So I have minus 31. So minus 31, I'm going to round to minus 34. So I'm going to choose PG 64 minus 33. So if I'm going to choose reliability 98%, then my cement asphalt binder is going to be PG 64 minus 34. Alternatively, if I'm going to choose 50% reliability, then the value of Z is going to be 0. So this one is 0, this one is 0. I'm going to have only the mean value. So the mean value is 56. Then I'm going to go here. I have 56. I'm going to round to 58. So my PG is going to be PG 58. Regarding the lower temperature, I have minus 26. So here I have PG 58. Here I'm going to look for minus 23. So minus 23, I'm going to round this to minus 28. So my PG is going to be 58 and minus 28 if I'm going to use reliability 50%. So I'm going to give you another example here. Please focus here. What is the standard PG asphalt binder grade should be selected under the following conditions. So here I'm going to give you conditions, and then you need to select the suitable PG asphalt binder. They say that the 7-day maximum pavement temperature has a mean of 57 degrees Celsius and a standard deviation of 2 degrees Celsius. So he measured the maximum temperature, he give you the mean value, he give you the standard deviation for it. Also, he measured the minimum pavement temperature, and the mean came out to be minus 6 degrees Celsius, and the standard deviation is 3. And he said that he wants reliability of 98%. So in this case, what should I do? I'm going to use this formula again. So since the reliability is 98%, that means the value of Z is going to be 2, and here the value of Z is going to be 2. For the maximum temperature, the mean value is 56, and the standard deviation is 2. So this one is 57 plus 2, which is the value of the Z, plus 2, which is the value of the standard deviation. So this one should be 61. So if then you are gonna get back to the table here. You have 62, 61. Then you are going to choose a PG 64, right? Because this one is the nearest to 61. So here the high temperature, I'm going to substitute in this formula. The value should be more than or equal 61. The nearest one is PG 64. Now I'm going to look for the lower temperature. The mean value is -6, and the value of Z is 2 because I have reliability of 98%, and the sigma is given here, which is 3. Then the lower temperature should be less than or equal -12. So then again, I'm going to get back to the table here. I'm going to look for my value. The value here is -12. So -12. The nearest one is -16. So I'm going to choose -16. So here, the final PE is going to be 64 and -16 is how we choose the values. Okay. So before I'm going to talk about the asphalt concrete, do you have any questions regarding how to solve or how to choose a suitable PE asphalt? Okay. If you don't have any question, I'm going to continue. So uh, we learn how to choose the asphalt binder using the performance grading, the PE system. So in the PE system, you need to know the maximum and the minimum values. Also, you need to know the mean value and the standard deviation. You need to know the probability. And if you know the probability, then you are going to use statistical models. You need to know the value of Z and so on. This is how we choose the asphalt binder. But why we should select asphalt binder? Because we are going to use asphalt binder in order to produce asphalt concrete. Asphalt concrete is composed of asphalt binder plus the aggregate. So the asphalt concrete, also known as the hot mix asphalt, because in order to mix them together, you need to heat the asphalt binder and also you need to heat the aggregates. So the asphalt concrete consists of the asphalt binder and the aggregates. They are going to be mixed together at high temperature and then placed and compacted on the road while still hot. This is the asphalt concrete or the hot mix asphalt. So what is the objectives in a proper hot mix asphalt? If I'm going to produce hot mix asphalt, what are my objectives? First, I need to have stability or resistant to permanent deformation and the action of traffic loads, especially at high temperature. So my asphalt should be stable enough so that it can resist the deformation under the action of traffic loads. Also, my asphalt should have fatigue resistance to prevent fatigue cracking under repeated load. Fatigue, which means that my material is going to get tired through the years, is not going to take the same load as before. We call this fatigue. So should have fatigue resistance. Also, we should have resistance to thermal cracking that might occur due to contraction at low temperature. The thermal cracking especially take place at low temperature because the material is going to be too brittle, and that is going to then the asphalt concrete is going to be susceptible to thermal cracking. Also, we should have resistance to hardening or aging during production in the mixing plant and in the service. Also, we should have resistance to moisture-induced damage that might result in stripping of asphalt from aggregate particle. Moisture-induced, it means that sometimes maybe you have moisture or water, and that the action of the moisture and the water with the traffic is going to cause a problem. The aggregate is going to separate from the asphalt binder. Also, we should have skid resistance by providing enough texture on the pavement surface. So if you are driving a car, if you press the brake, then you should have skid resistance so that your car is going to stop. Otherwise, it's going to take a lot of distance, and that may result in accidents. Also, during the mixing and placing of the asphalt, you should have workability, good workability. Otherwise, the mixing process and the compacting process is going to be very. So the purpose of the asphalt concrete mix design. Why should make asphalt mix design. We know that if you are going to mix aggregate with the asphalt, then you are going to get asphalt concrete. So why we should learn how to come up with asphalt concrete? So the purpose of the asphalt concrete mix is to determine the maximum asphalt content. We need to determine exactly how much asphalt binder we need for our asphalt concrete. So of course we are going to use locally available asphalt and aggregate. So if the appropriate design asphalt content is not used, if you are not going to use the optimum amount of the asphalt, then the pavement will lack durability or stability. So if you are not going to choose the appropriate amount of asphalt, then you are going to have either problem in durability or problem in stability. How we are going to have problem in durability? If you are going to use too little binder, then not all the aggregate is going to be coated. So you are going to lose some of the aggregate. So you are going to have durability problem. Maybe after 1 year or 2 years, your road is going to be destroyed, right? Because you didn't use enough amount of asphalt. So the aggregate is not going to be coated well, okay? Then what if I'm going to use a lot of amount of binder? So too much binder, that means too much lubrication. That means the stability is going to be in a problem, right? Because if you use a lot of asphalt, then the aggregate, when the action of the load, then the aggregate is going to have a lot of deformation. So also you are going to have a problem. So do not put a little binder. Also do not put a lot of binder. You need to choose the optimum amount or the appropriate amount. So what is appropriate amount? The typical asphalt design asphalt content range from 4% to 7% by the weight of the total mix. Of course, we talked about this in the lab last time. We said that the optimum amount of asphalt is going to be between 4% and 7%. We are going to try to use quantities from 4% to 7%. We are going to produce many samples in order to select the optimum value of the asphalt binder. So in order to come up with asphalt concrete, we have 3 methods of asphalt mix design. We have the Marshall method. This one is empirical, which means that this method does not depend on the performance. This all just is empirical. And this one is more common. In our lab, the last lab, we use the Marshall method in order to produce asphalt concrete. Also, we have Havim method. This one is also empirical, just like the Marshall method, but this one is the less common. Finally, we have the super pave method. We say that this method, it has been introduced in 1987, and this method depends on the performance. Is the best method right now, and most of the DOH, the Department of Highways across the countries, are now using the super pave. Although it's much more rigorous. So this one is accurate. It requires a lot of tests. So it's not easy to come up with super pave asphalt concrete using super pave method. And the super pave method depends on 2 components. It has volumetric design, and it has also performance testing. So nowadays, most of the Department of the Highways or the municipality, those who are responsible for making roads, nowadays they are shifting to use the super pave method. Okay, this one is better, even though it requires more tests. Here in this city, in Medina City, the municipality use the Marshall method, while the innovation department, those are responsible for making the Medina better, they are using the super pave method. Also, the Ministry of Transportation, they are using the super pave method, and the municipalities using the Marshall method. Okay, but the future, of course, for using the super pave method. So before we talk about the how to produce concrete asphalt, it's important to talk about the density and the void analysis. Okay, so it's important to understand the density and the void analysis of compacted asphalt mixtures for both mixed design and construction control. So regardless of the method, whether you use Marshall or Havim method or Super Brave method, you need to understand the density and the void analysis. Okay, so regardless of the method used, the mixed design is a process to determine the volume of asphalt binder and aggregates required to produce a mixture with the desired properties. Okay, so it's important to understand this. However, since volumes are difficult and not practical to measure, weights are used instead. So here we talk about the void analysis, which means that we need to know the volumes, and it's very difficult to measure the volumes. So we are going to use the weights, and in order to relate the volume and the weights, of course, we have the specific gravity. The specific gravity is going to get in between. So we are going to convert everything through the specific gravity because like we have learned through this semester and in the lab, we managed to determine the different type of specific gravity. We can determine the specific gravity for the aggregate. We can determine the specific gravity of the asphalt cement. We can determine the specific gravity for a mixture. For example, I can use the theoretical way in order to determine the specific gravity. So now we have three important parameters commonly used. So we have the percentage of air voids or voids in total mix, VTM, this one here. Also we have the voids in the mineral aggregate, VMA, and we have the voids filled with the asphalt, VFA. So here we have the representation. Of course, this one is an imaginary representation for the asphalt mixture. The asphalt mixture is we are going to have aggregate, and we're going to have asphalt binder. Of course, some of the asphalt binder is going to be absorbed by the aggregate. So we call this the absorbed asphalt binder by the aggregate because we know that the aggregate contains void. So when I'm going to mix the aggregate with the asphalt, some of the asphalt binder is going to be absorbed by the aggregate. And of course, we have air voids. We put this like that so that we can understand the analysis. But in the reality, all of this is going to be mixed together, right? I'm not going to find the air voids alone and the asphalt alone and the absorbed asphalt alone and the aggregate alone. But we made it like that so that we can understand the different types of voids, okay? So if I'm going to have asphalt mix, I'm going to have aggregate, I'm going to have asphalt binder, I'm going to have asphalt binder absorbed by the aggregate, I'm going to have air voids. So here V sub V represent the air voids, V sub BE represent the volume of the asphalt binder. This one is effective. And from here to here represent the volume of the aggregate. From here to here represent the weight of the aggregate. S it means solid. The solid part is the aggregate, and here is the weight of the binder effective. Okay, if I'm going to sum all of this, I'm going to have the V sub M, the volume of the mixture, the total volume. If I'm going to add this one plus that one, I'm going to have W sub M, the weight of the mixture. So the asphalt mixture consists of course, aggregate, asphalt binder, and air voids, like you can see here. Note that a portion of the asphalt is absorbed by the aggregate particles. So this one here is going to be absorbed by the aggregate particle. First, we need to determine VTM, the voids in the total mix. So in order to determine the void in the total mix, from here to here represent the total volume VM, and this one is the air voids V sub V. Then if I'm going to determine the void in the total mix, then I'm going to divide V sub V over VM. So VTM is V sub V over V sub M. I'm going, in order to convert it to percentage, it need to be multiplied by 100%. So VTM is easy. Then I have VMA. VMA voids in the mineral aggregates, which means that if I put the aggregate only, then what are the voids is going to be resulted from the aggregate. So if I'm going to fill this only with aggregate, okay, then I need to know how much void that I'm going to have, okay, which means that I'm going to ignore the asphalt binder and the air voids. All of this is going to be like a voids for me because I need to know only the voids because of the aggregate. If I put the aggregate alone here, I need to know the voids. So in this case, the V sub V and VBE is going to represent the voids because of the aggregate. If I put the aggregate alone, then this one is going to be a void, and this one also is going to be voids. So VMA is going to be V sub V plus V sub BE over the VM, the volume of the mixture. This one is the VMA, the voids because of the mineral aggregates. Finally, I have the voids filled by the asphalt. So here I have a void. I have this void here because of the mineral aggregate. I want to know how much void has been filled by the asphalt. So now from here to here represent the voids because of the minerals aggregate, which means that V sub V over plus V sub BE. Okay. Then I want to know how much voids has been filled by the asphalt binder. So this one is going to fill the voids of the aggregate. So VFA is going to be V sub BE over this one plus that one, V sub V plus VBE. So this one represents the voids that has been filled by the asphalt because of the aggregate. So I have VTM, I have VMA, I have VFA. So those are important in order to make void analysis, because then the criteria in order to choose the best mix depends on those values. After we determine those values for a certain specimen, we need to compare this with the criteria, which mean that I have a certain values. If my values more or less than those values, then I'm going to reject my specimen. So as stated before, since volumes are difficult to measure, weights are used instead. So we are going to use the weights, and that it could be done by converting using the specific gravity values. We have different type of specific gravities. We have GMM. This one is the theoretical maximum specific gravity of the asphalt, and this one could be determined with this value. So GMM is going to be the percentage of the solid, which means that the percentage of the aggregate over GSE. GSE is the specific gravity of the asphalt coated with the aggregate coated with asphalt, which means that the aggregate is going to absorb the asphalt, plus P sub B, the percentage of the binder over the GB. GB is the specific gravity of the binder. So GB is the specific gravity of the binder. GSE is the specific gravity of the aggregate, but should be coated by the asphalt. If I'm going to ignore the absorption, in this case, GSE is the same as GSB. So the effective asphalt gravity of the aggregate is going to be the same as the specific gravity of the aggregate. So this formula will be able to determine GMM with the theoretical maximum specific gravity of the asphalt concrete. P sub B sub S and P sub B. This one represents the percentage of the solid, which means that it's the aggregate, and this one represents the percentage of the binder. If you add this one plus that one, it should be 100%. So then we are going to relate these volumes to specific gravity. So through mathematical processes, we are going to convert VTM from using volume to using the specific gravity. Similarly for the VMA and for the VFA. So I'm going to convert this one. Instead of using volumes, I'm going to use a specific gravity, similarly here and similarly there. So in order to use this formulas here, I need to know the value of GMB and GMM. How to determine GMM? From here, from this formula. How to determine the GMB? In order to determine the GMB, this one should be done in the lab. I'm going to use this formula. GMB is going to equal A over B minus C. A represents the dry weight of the sample, B represents the saturated surface dry weight, and C represents the submerged weight. So if I know those values, I'll be able to determine GMB. GSB represents the bulk specific gravity of the aggregate, and if you are going to ignore the absorption, then GSB is the same as GSE. So if I know GMB from this formula and I know GMM from that formula, then I will be able to determine VTM. Then what about VMA? VMA depends on GMB, which is here, depends on the PS, the percentage of the solid. This information should be known, and also depends on GSB, which is here, the bulk specific gravity of the aggregate. then I'll be able to determine VMA. Then VFA depends on VMA and VTM. So if I know VTM and VMA, I'll be able to determine VFA. Okay, so now we convert this one here into specific gravities. So if I have a certain example, I should be able to determine all the specific gravity. Then I will be in a position in order to determine VTM, VMA, and VFA. So let's see this example here. In example number 1, we have an asphalt concrete specimen has the following properties. So in this problem here, asphalt concrete specimen has been produced with the following properties. First, the asphalt content that it has been used in order to produce this asphalt concrete is 5.9% by the total weight of the mix. So this one here, this represent the P sub B, the percentage of the binder. If this one is 5.9%, it's mean that the P sub S is going to be 94.1. Okay, because I need to subtract this value from 100%. And here it says that the bulk specific gravity of the mix is 2.457. This one represents the value of G of MB. Okay, this one is specific gravity of the mix. Here we have the theory. This one represents the value of G sub SB. Now we need to determine the VTM, VMA, and VFA. In this example, it's going to be straightforward because we have all the values. So I'm going to see the solution. So in order to determine VTM, we say that VTM is going to be expressed in terms of a specific gravity. So VTM equal 100% bracket 1 minus GMB over GMM. So do I know the value of GMB? Yes, it's given here, which is 2.457. Do I know the value of GMM? Yes, it's given here, which is 2.598. So this one is going to be straightforward. I'm going to substitute the numbers into the formula. This one is given here, and this one is given there. So the VTM, the volume in the total mix is 5.4%. Then I'm going to determine the VMA. Again, I'm going to use the formula. This one is going to be straightforward. VMA is going to be 100% minus GMB times PS over GSB. Do I know G sub MB? Yes, it's given here, which is 2.457. Do I know GSB? Yes, it's given here, which is 2.692. What about the value of PS? PS is going to be 100% minus the asphalt content. Okay, so because we say that P sub S plus P sub B should be 100%. So now I've got everything here. So I'm going to just plug the numbers into the formula. This one is going to be 100% minus 5.9. This one is given, and that one is given. Then the VMA come out to be 14.1%. Finally, the VFA. The VFA depends on VTM and VFA. If I got VTM and I got VMA, then easily I can determine VFA. So VFA is going to be the VMA minus VTM over VMA. So just I'm going to block this number and that number into this formula, and then the value of VFA came out to be 16.7%. So this example is a direct example. It's direct, straightforward. It can be easily solved. But now look at example 2. Example 2 is a little bit complicated than example 1. Well, example 2. So let's see how we are going to solve. The givens is going to be different than example 1. So here we have example 2. In example 2, we have compacted asphalt concrete specimen contains 5% asphalt binder. So this one is going to represent the value of P sub B, which is 5%. That means the value of P sub S is going to be 95%. And also the specific gravity of the binder is given here. The specific gravity is 1.023. So also specific gravity of the binder. So G sub B is 1.023. We have aggregate with a specific gravity of 2.755. So the value of the specific gravity of the aggregate is given also, which is G sub B. And here he gave us the bulk density of the specimen. So this time he didn't give us the specific gravity of the bulk. He gave us the density of the specimen, which is 2.44 mg per cubic meter. It says here ignore the absorption. If we are going to ignore the absorption, it's mean that the value, the GSE is the same as GSB. So here we have the density of the bulk came out to be 2.441 mg per cubic meter. So since the problem stated that ignore the absorption, then the GSB is the same as GSE, like we just mentioned. So first we are going to determine GMM. So we are going to take advantage of this here. The GSB is the same as GSE. We are going to determine G sub MM, the theoretical maximum specific gravity of the mixture. We are going to use this formula. We have the P sub S. This one is going to be 95% because this value is 100% minus 5%. And the value of P sub B is 5% is given here. The value of GSE is going to be the same as the value of GSB. So this one is going to be 2.755, while the value of GB is given here, which is 1.023. So the GMM came out to be 2.54. So now it's important for me to determine GSB. So GMB in general, it's the density of the material over the density of the water. Here, the density of the mixture is given, which is 2.441, and the gamma water, in case that you are dealing with mega gram, this one, okay? So if you are going to determine the density of the aggregate using mega gram, so this one is going to be only 1. So if I'm going to use the general formula for the specific gravity, which is the density of the material over the density of the water, this one is going to be only 1, which means that the G sub MB came out to be 2.441. So now I got the GMM and I got the GMB, then I'm in position in order to use the formulas in order to determine the different values. So I'm going to use this formula again. I'm going to use VTM. VTM is 100% bracket 1 minus GMB over GMM. I already determined GMB and I already determined GMM. So I can easily just substitute my numbers in this formula and I'm going to get VTM. So is going to be 1 minus GMB over GMM. I already determined GMB, which is 2.441. I have GMM, which is 2.45. So the VTM came out to be 3.9%. Similarly, I'm going to use a formula for VMA. In the formula of VMA, I have 100 minus GMB, which I already determined. I have the, I should know the value of GSB. This one is given. And PS is also given, which is 100% minus 5. So I've got all I want. Then I'm going to just plug the numbers in the formula, and the answer came out to be 15.8%. Finally, in order to determine VFA, since I know VTM and I know VMA, I can easily plug the numbers in the formula here. I know the value of VTM 3.9, VMA is 15.8, then the value of VFA came out to be 75%. So since I know the value of GMB, GMM, and GSB and PS, then I'm in position in order to determine the main three parameters, the VTM, VMA, and VFA. So this is how we are going to conduct a void analysis. Whatever the methods that you are going to use in order to produce asphalt mixture, it's important to understand the different type of voids. So quickly, I'm going to talk about the Marshall design method. Marshall design method is the empirical method, but it's more common. And nowadays, people are replacing the Marshall design method with the super brave method, which is more accurate, but it required a lot of calculation and experiments. So in order to produce asphalt mixture using Marshall design method, you need to evaluate the aggregates, you need to evaluate the asphalt cement before you are going to use them, you need to evaluate them. So the aggregate characteristics that must be evaluated before it can be used for an asphalt concrete mix include the durability, you need to test the durability, the soundness, the presence of deleterious substance, you need to evaluate the shape and the texture. Agency specification define the allowable range for the aggregate gradation, which means that you need to conduct safe analysis so that to know your aggregate within the appropriate range of gradation. Also, you need to evaluate asphalt cement. So the grade of the asphalt cement is selected based on the expected temperature range and the traffic conditions. Regarding the specimen preparation, in order to perform a full Marshall mix design, you need to have 18 specimen. Okay, the diameter should be 4 inches, and the height it should be 3 inches. And then you need to determine the stability and the flow. You are going to use the Marshall device for 15 specimen, because the 3 specimen should be used to determine the theoretical maximum specific gravity. So in case that I don't, in case that I didn't ignore the absorption, in this case I need to conduct additional experiment in order to determine the GMM. The GMM is going to include asphalt aggregate with asphalt binder. Also regarding the Marshall stability and flow measurement, the Marshall stability of the asphalt concrete is the maximum load the material can carry when tested in the Marshall apparatus. And also the test is performed at a deformation rate of 51 millimeter per minute and the temperature of 60 degree Celsius. The Marshall flow is the deformation of the specimen when the load started to decrease. In other words, the Marshall flow is the deformation corresponding to the maximum load the material can carry. Finally, we need to conduct density and the void analysis, which means that you need to determine the value of VTM, VMA, and VFA. So after you finish for all of this, you need to come up with all of these graphs, about 6 graphs. You need to show the relation between the air voids and the asphalt binder by weight, the density and the asphalt binder by weight, the flow versus the asphalt binder by weight, the Marshall stability versus the asphalt binder by weight, VFA and VMA. After that, you need to design based on 4% of the air voids. Then you are going to get the corresponding asphalt binder. The values that you are going to get here, you are going to determine the Marshall stability based on that value, VFA based on that value, and VMA and the flow and the density based on that value that you got from 4%. Then you are going to compare the values with the criteria here. You have the traffic level, whether it's light or medium or heavy. It depends on the compaction, the blows that is going to be applied to your specimen. Then you are going to compare with the stability. You have maximum, you have minimum for the stability and for the flow. And then if your numbers is going to meet the criteria, then your mix is okay. Otherwise, you need to come up with changes so that the numbers is going to meet the criteria. So I'm going to stop here. So if you have any questions, please ask me.